Did you know that ships use bubbles to help them glide through the water? Bubbles are actually a game-changing technology that cuts down resistance, saves fuel, and reduces greenhouse gas emissions. Welcome to the fascinating world of the air lubrication system, or ALS, where tiny air pockets are the unsung heroes of shipping innovation. In this video, we'll explore the science and impact of this remarkable technology and how it's making waves, well, bubbles, in the shipping industry. The US Navy started using a technology that created a constant stream of bubbles around a ship's hull after World War II. They did this to mask the noise from the ship's main engine and other machinery, so enemy ships wouldn't detect them. Over time, scientists became curious about how air bubbles affect a ship's frictional resistance, leading to the development of air lubrication technology. Before we dive into that, let's break down what we mean by resistance. When a ship moves through the water, it gets pushed back by the water around its hull. To maintain speed, the propeller has to generate enough thrust to fight against these opposing forces. Understanding the resistance characteristics of a hull is crucial in modern ship design because it directly affects fuel efficiency, speed, and overall performance. Back in 1861, English engineer William Froude suggested that resistance has two main parts: wave-making resistance and frictional resistance. When a ship or any object moves through the water, it pushes the surrounding liquid aside, which creates waves. The energy used to make these waves slows the ship down, which is why it's called wave-making resistance. Then there's frictional resistance, caused by the friction between the water and the ship's hull. This is sometimes called plank friction. By towing wooden boards of various sizes underwater behind boats at different speeds, Froude realized that even though the planks were under the waves, they still had a force pushing back against them. That meant it couldn't be the waves alone that were causing resistance. It had to be the friction caused where the wood meets the water. He worked out that the frictional resistance of the surface area of the part of the hull that's underwater is the same as he found on the wet part of his planks. Of course, there are other components too, like air resistance. The parts of the ship above the waterline face air resistance, just like planes and cars. However, unlike those vehicles, air resistance only makes up a small part of the total resistance force. The resistance from water on the submerged part of a ship is much larger because water is about 800 times denser than air. Then, in 2011, the International Maritime Organization rolled out a new measure requiring ships to boost energy efficiency and cut greenhouse gas emissions. This is known as the Energy Efficiency Design Index, or EEDI. Shipbuilders now focus even more on cutting down resistance because reducing resistance helps meet these new environmental standards. There have been some great advancements in hull form design over the years. Wave-making resistance isn't as important as frictional resistance. In fact, frictional resistance can make up to 85% of the total resistance in low-speed vessels, including most merchant ships. So, technological progress that cuts down frictional resistance can lead to even bigger fuel savings. The air lubrication system is one of these technologies. As mentioned earlier, the frictional resistance of a ship is considered to be equal to the resistance of a flat plank with the same wetted surface area. The frictional drag comes from the contact between the water and the hull. That drag is actually stronger between solid and water than between solid and air or air and water. The ALS cuts down this frictional drag by putting air between the water and the hull's surface, reducing the area of the hull that's in direct contact with the water. That's why it's called the air lubrication system. The air acts like a lubricant between the water and the hull. There are a few ways to achieve this effect. One way is by injecting air under the ship to create an air layer. When the injection starts, the air forms a continuous layer at the bottom, separating the hull from the water flow. As more air is injected, it can maintain a fully continuous air layer over a large part of the wetted surface area, significantly cutting down frictional resistance. Another method, although less popular, is partial cavity drag reduction. Developed by the Russian Navy, this involves creating a cavity under the ship to form the air layer. Remember when you were a kid and you put a glass upside down in water and the water didn't get inside? It's the same idea. In practice, the air inside the partial cavity gradually escapes as the ship moves, so it needs a constant air supply to keep the air layer. But tests show that the energy needed to maintain this air layer is only a third of what's needed to maintain a traditional air layer without the cavity. While you can cut frictional resistance down using an air layer, it's tough to keep that layer constant as the ship speeds up. Plus, it's not just speed increases that can disrupt it. rough seas can also weaken the layer's stability. So, now we get to bubbles. Besides hiding the ship's noise, you can also use microbubbles to reduce frictional resistance instead of a continuous air layer. The big difference between this system and the air layer system is that the air layer system cuts down frictional resistance by decreasing the hull surface area in contact with the water, while the microbubble system changes the density of the water around the hull. The microbubble system has some advantages. It doesn't require you to manage the stability of the stream like the air layer system does. Plus, it takes less energy to create the bubble stream than to form an air layer. Another big benefit is that you can generate microbubbles all over the hull, not just on the flat bottom. Tests show that for the ALS to work its best, the bubbles should be really tiny, often less than 0.1 millimeters in diameter. But in practice, controlling the bubble size is difficult. Even when the bubbles are the correct size, they tend to merge and form bigger bubbles downstream. Since the microbubble system works by altering the properties of the water in contact with the hull, it's crucial to keep the bubble stream close to the hull. As the bubble size increases, it becomes more challenging to maintain contact between the bubble-water mixture and the hull due to the buoyancy of the bubbles. ALS is also cost-effective. They can be easily installed on existing ships without major modifications to the hull. They're also more energy efficient than other energy-saving methods, like rotor sails or PV panels. But unlike those renewable sources, an air lubrication system still needs extra power to run the blowers and compressors that supply air. While you save energy by reducing frictional resistance, you lose some energy powering the machinery. To account for this energy loss, the International Maritime Organization states that the power needed to run ALS should be subtracted from the power reduction when estimating the reduction factors for EEDI certifications. So, how effective are air lubrication systems? Different manufacturers provide different estimates for their technology, but sea trial data from 2002 to 2015 found that air lubrication systems can save up to 10% in net energy. When used alongside other fuel-saving technologies, an air lubrication system can significantly boost the ship's energy efficiency.